Hello everyone, welcome to Tech Talk session number 20. Paul Stechik with NEPSI. And today we're going to finish up this two-part series on harmonic filter design, how to determine component ratings. So some housekeeping things first. Don't forget at the end of the presentation we will give you a code for PDH credits. Just send us an email, we'll get you a PDH credit back. Don't forget to tell others about this great opportunity to learn a little bit about the harmonic filters, reactive compensation, all to medium voltage level, and share that with your colleagues and let them know that this is a great way to learn and also receive PDH credits. We typically get those certificates back within the hour, so it's really a great way. We're going to flash over real quick to Rodrigo Dunner. He's located in South America and in Chile, and incidentally, in Chile is about to go into their Independence Day, so Rodrigo is about to hop onto a long weekend here. So Rodrigo is located in Santiago, and he's with us to help with translation for those located in Latin America. If you have questions, Rodrigo is here to answer those questions. So Rodrigo, perhaps just introduce yourself again and let them know what you're up to.
Okay, perfecto. Bueno, Paul, thank you very much for this opportunity. Y bienvenidos todos las personas de habla hispana a nuestra Tech Talk, NEPSI Tech Talk. Muy brevemente, soy el encargado de ventas, marketing y desarrollo de negocios internacionales y nacionales en Latinoamérica para NEPSI. Nosotros desarrollamos y fabricamos filtros de armónicos y bancos de condensadores metal enclosed para diferentes aplicaciones y adicionalmente estudios como por ejemplo estudios de armónicos y de factor de potencia para los proyectos que desarrollamos. En relación a la experiencia, tenemos más de 2.000 unidades que hemos desarrollado, fabricado e instalado en nuestros últimos 25 años, de los cuales 100 proyectos han sido en minería y 55 de gran envergadura. De esos 55, 30 se encuentran entre Chile y Perú en importantes plantas de concentración y electrowinning. Finalmente, y muy brevemente, tenemos también un área de servicio técnico y servicio de asistencia técnica en Latinoamérica, basado en Chile, bajo el comando de Patricio Guzmán, para todos nuestros clientes con los cuales hemos desarrollado proyectos en esta región. Y si tienen dudas o consultas, requieren apoyo para cualquier tipo de proyecto o tienen dudas con respecto a especificaciones técnicas, lo que necesiten, por favor contáctenme rodrigo.dunner@nepsi.com, Dunner con 2N. Muchas gracias.
Okay, thank you, Rodrigo. And don't forget, you can contact Rodrigo at rodrigo.dunner@nepsi.com. He's located in Latin America, and he helps always with our translation. So we ship quite a bit into South America, and he is a key factor in accomplishing that. So last week, we had a question. I deferred the question to this week, and I want to go through that question real quick. So perhaps I can go to my iPad here. And I hope the individual that asked that question is still around on this week's presentation. So the question really was in regards to the resonance that occurs due to cable capacitance. And I kind of drew a quick collector system here. So I have a source here and a collector, a step-down transformer from a high voltage level, and a 5th, 7th harmonic filter I have here, and then the collector system, and out here there might be some turbines. And so as you know, or many of you should know, is that when you have a medium voltage cable, there is capacitance that exists between the inner core, the copper conductor here, and the shield that surrounds the cable. And that is a line to ground capacitance. And basically the question last week was, well, that's a line to ground capacitance. Does that enter into the positive sequence network? And the answer to the question is yes, it does. It does enter into the resonance calculations, and it's really the balanced portion of that capacitance that's going to make it into the resonance. So down here I had drew an impedance curve for the system, and I have a Z here, harmonic number here in this direction. And typically that cable capacitance, it's usually maybe a megavar on a typical wind farm, or 2 megavars at most. When you have a harmonic filter system installed here, in this way I have a 5th and a 7th, so we know that because of the low impedance that exists here at the 5th and here at the 7th. and we will get another rise in the impedance scan, and that will be resonance caused by the cable capacitance here, which is really a combination of all that distributed capacitance within the cables, and sometimes it's many, many miles. That will cause a resonance, and really it's the balanced portion of that capacitive impedance, which if it's cables, it's going to be very balanced capacitance, and it will show itself in the positive sequence network. So the answer to that question is yes, it does show itself, and the harmonic analysis programs do account for that, is what we found. So I did defer to somebody else to make sure that my thinking was correct on that. So last week we went over harmonic filter design. This is a two-part session, and if you missed it, you can still go to youtube.com/NEPSI. We have a playlist there, and it will have all the videos, all the Tech Talk sessions, and this is our 20th available for you to watch. So you could watch Tech Talk session number 19. I also mentioned Tech Talk session 9 because NEPSI has a spreadsheet tool on a website that really parallels all the information that you obtained in this presentation here today. So make sure that you also watch Tech Talk session 9 if you are involved with harmonic filter design. So I'm not going to go too much into what we talked about last week. I think that you would be better off to go through it in detail. But last week we got to the point where we were talking about the tuning calculations, and we reviewed three types of filters: the notch harmonic filter, the high-pass harmonic filter, and the C high-pass harmonic filter. The tuning point calculation, okay, is about the same. It's the same exact concept. We are always looking to calculate X effective, which is basically the total impedance across the harmonic filter based upon a value of Q effective, which is the output kVAR. When you're specifying harmonic filters, always remember there's an installed kVAR, which is based upon the capacitance here, and capacitors are always rated by voltage rating, terminal to terminal, which is typically like a line to neutral value, but not typically in a filter, slightly off of that. And it's kVAR rating. So you got frequency, you got volts, and you got kVAR rating, bushing to bushing. And so normally when you look at a harmonic filter, the installed kVAR is always greater than the output kVAR here. We're going to have a higher installed kVAR. So when you're specifying harmonic filters, be sure to distinguish between installed kVAR within the capacitor itself and the effective kVAR, the kVAR output of the harmonic filter. If I put terminal voltage here, what is the kVAR output? And really, that's a key filter parameter. So we go through this process and we come up with a value of X of C, and from there we pick a capacitor. And we're going to talk about how to choose a capacitor on that basis. We go further down, we have inductance. We're going to talk about, well, how do you determine what that inductance is? How do you specify that iron core reactor? We give you our philosophy in this paper, in this Tech Talk session. And we have some other parameters, the fundamental rated current of these various components, and then the RMS current rating. So we're going to be talking about how we distinguish, how we come up with those components. A high-pass filter is exactly the same calculation. Really, the only thing that changes is coming up with this value of resistance, which is really determined during a harmonic study. We need to have a dampening factor when we're doing the study. We're coming up with a value of resistance. Remember, you always want to design first for notch filters. Try to see if you can get through a system and have a good performance with notch filters, because they are the simplest and most cost-effective filter design. But when the system has, say, interharmonics, or there are concerns for resonance associated with stray capacitance, then we oftentimes go with high-pass harmonic filters, and we add this value of resistance here. That value of resistance is determined first during the study simulation process. We're determining, well, what value of R do we need? Usually the process starts where you start with a high value of R, which if you think about a high-pass filter, if it's an infinite R, then it's a notch filter. We start to decrease the value of R, and we look to get adequate performance. As you decrease R, the losses in that resistor go up, and that's really the issue here. We're trying to minimize the losses, the 60 hertz or 50 hertz losses, that fundamental losses within the system. So this is part of the harmonic filter design process, is done through trial and error with the simulation software package, whatever that may be. So, and we have a C-high pass filter. Remember, we talked about this last week. C-high pass filters and high pass filters have the same characteristic curve. They have the same characteristic curve. The only difference is this value of X of CA here. And that value of X of CA is put in place where it exactly equals X of L at its tuning frequency. No, not as tuning frequency, but at its fundamental frequency. So X of CA equals X of L at the fundamental, whether it's 50 hertz or 60 hertz. So again, we're starting with this concept of Q effective, using the value of X effective, and then coming up with X of L, X of CA, and X of CM. These are the equations. I can tell you we always use a spreadsheet tool, and that's why I referred you to session 9, because you typically have a spreadsheet tool to have you walk through this type of calculations. So we're going to move on to, well, here is the spreadsheet tool. So this is the easy way to do it. This is the way we do it. It's on our website, and session 9 will go through the process of picking up components. We have some recommendations, and the first recommendation when selecting the component ratings is to be very conservative. Okay, and the reasons being is that you have a harmonic study, you come up with what you think is the harmonic current flow into the filter, and from there you're choosing components, the reactor ratings, the capacitor ratings, the capacitor voltage rating, and so on. Is based upon simulations, which is kind of an ideal world. We've made assumptions during the simulation process. The question is, are the assumptions all correct 100%? And normally they're not. There's errors in your simulations. There's errors in the data that you assumed, or the data that was provided to you by the utility or the drive supplier. So normally you want to be conservative with your design for that reason, because you actually might get more harmonic current flow into your filter. You might test those components a little bit more. So you want to be very conservative with your design. The other thing is to remember that systems do change. You design a harmonic filter for today. Well, in the future, after the study is long gone and done, the harmonic filter is installed. It could be 5, 6, 7, 10 years later. That mine or that industrial facility might say, well, I want to expand. I want to add more drives. I want to add another compressor. I want to add another grinding mill. And that means more harmonic current to the system. And it might not necessarily mean that they need more reactive power. So you want to make sure that that filter design can handle that additional harmonic current that might become available in the future. If you don't do that, then the filter is at risk. It's at risk of burning up. You add more filters to a system where the filters are marginally rated, more harmonic current sources to a system that has a marginally rated filter, it's going to potentially get hot and burn up. So the cost to increase component ratings is pennies on the dollar. It really is, and I kind of show that over here. You already have a reactor that's custom made. You have potentially capacitors that are custom made. You're buying a whole harmonic filter system that is custom made. So to add additional ratings to the reactors, to the capacitors, is really going to cost you pennies on the dollar. So we highly recommend that you put a significant amount of harmonic current rating and harmonic voltage rating on the components. So we're going to talk about that as we move along in this presentation. You want to make sure that you use reputable manufacturers. Okay, who are you buying reactors from? Make sure that those reactors are being supplied by a company that is in the business of supplying harmonic filter reactors. Harmonic filter reactors, even whether they're air core or iron core, it's a different phenomenon. It's not like a transformer. Oftentimes, engineers, especially those developing specifications, will feel that if you can build a transformer, you can build a tuning reactor, and you cannot. They're totally different. Much more difficult to build an iron core harmonic filter reactor. So in the U.S., there's just a few reactor suppliers that we have vetted and approved as our suppliers, and we just have one in Europe. So there's not a lot of suppliers out there. You want to make sure that you pick one that is in the business of doing harmonic filter reactors. Ask, what tests do you do? How many have you produced? Those types of questions. So, and this will be same for capacitors. You want to use capacitors that are from reputable suppliers. So NEPSI will use one of three different capacitors from one of three North American suppliers. So we're going to talk about capacitors first. You know, filters are composed of capacitors, reactors, resistors. So there's not a whole lot of components here. We got the fusing and the switching device. We have some other tech talks that we've discussed. The switching devices, the switches or the breakers that we utilize. So today we're just going to be talking about capacitors, reactors, and resistors. So first of all, the capacitor standards. We are purchasing from suppliers in the U.S. We are typically following this IEEE standard 18 here, and that you want to buy capacitors that apply to those ratings. Canadian, we have C22.2, and if you're going into IC world, into Europe, and sometimes in South America, we're going to be buying capacitors that are designed and built in accordance to those standards. By and large, these standards are very similar, and really the way the capacitors are built and tested is kind of how we're picking capacitors. We're picking capacitors that are tested according to the standards, and the ratings of the capacitors are being tested against the way the capacitors are being tested. So this is the process. There are some application standards. IEEE standard 1036. Dated 2010 is a guide on the application of shunt power capacitors. It's a good reference for those that are looking to get more information. You got a IEEE C37.99 2012. The protection of shunt capacitors is another good standard. And then IEEE 1531, guide for the application and specification of harmonic filters. So for us, the main suppliers are primarily ABB, Cooper, General Electric. I do mention some others. VJ is a very popular capacitor supplier also that we have encountered in our years past. Capacitors can be either internally or externally fused. Here I show a capacitor that's externally fused. Okay, and by and large, NEPSI is utilizing externally fused capacitors. We do not use internally fused capacitors. One is not necessarily any better than the other. Our preference, and especially the preference in North America, is to use externally fused capacitors. We like them, and one of the key reasons is that the capacitor itself is simpler. There's not as many connections on the inside of that capacitor when the fuses are put external to the capacitor. The other thing is when a capacitor fails, it blows the fuse. It operates this fuse here. We can see that the fuse has operated. An indicator pops up. We know that the fuse has operated. So it's a preference thing. But I also believe that there's not a significant difference between these two types of capacitors. The most prevalent connection for medium voltage, 2.4 kV through 38 kV, is a ungrounded Y capacitor bank, or a ungrounded split-wye capacitor bank. So we won't really get into too much of what the difference between a split-wye and ungrounded Y is, but they're both ungrounded, and that's really the key here. They're both ungrounded. You would typically not want to connect a medium voltage capacitor to ground because it's introducing the zero sequence network into the system, and that's a more complex network. And you're dealing with now, with your filter design, you're dealing with zero sequence network and positive sequence network. So if we don't connect the filter bank to ground, we can ignore what's going to go on in that zero sequence network. So we're going to pick a filter capacitor based upon these four ratings here. So we're going to pick the filter capacitor based upon its RMS voltage, its peak voltage, is a nominal RMS current rating and is rated kVAR rating. Remember, the harmonic analysis program has calculated the harmonic filter current. I filter here. It's calculated the current flow through the capacitor. With that current flow through the capacitor, we are able to calculate these values here. All right, so we're able to calculate the voltage. It's just the filter current at each frequency times the capacitive reactance at that frequency. Remember, the capacitive reactance will drop off by the harmonic number. So the third harmonic will have 1/3 the value of X of C at the fundamental. So we can easily calculate the capacitor voltage based upon the harmonic current flow that would flow through that filter based upon a harmonic study. Remember, you want to add margin to your design, so you want to make the value higher. Typically, you want to add a significant amount of margin. So from there, our philosophy is that you want to rate this capacitor so that the voltage during normal operation is no more or no greater than basically 1 per unit, its rating. So when you put a capacitor in a filter, you get a voltage rise across the reactor, and that's counterintuitive. This capacitor will actually have a higher fundamental voltage than the line to neutral voltage here. Okay, so we have a higher voltage from the fundamental. We would have to account for that, and then you have to add to that all your harmonic voltages. Okay, so IF at the harmonic times X of C at the harmonic impedance, come up with the value of voltage, and from there we can calculate an RMS voltage. We would want that RMS voltage to be basically no greater than 1 per unit, the nameplate rating of the capacitor. Now, capacitors by standard can handle 110% voltage. They can handle 110% voltage, but when you do your design for your filter, you want to basically design the filter so that it's at 1 per unit, no greater than 1 per unit, that RMS value. That 10% voltage, additional voltage rating, is really for your system voltage regulation. The utility in your supply typically can be plus minus 10% voltage. So you need to hold on to that additional 10% voltage that the capacitors allow for the fundamental voltage of the system. The other test that you're going to be doing is 120% rated peak voltage. You're going to check, well, if all the harmonic currents, and this is really key here, all the harmonic currents, and maybe I'll go to the iPad here real quick. Okay, so you remember you might have multiple harmonic currents, and remember that I'm not going to be very good at drawing, but remember that the peaks of these harmonic currents, the 5th and the 7th and the 11th and so on, they have different phase angles, and you want to make an assumption that all the peaks are in line with each other, and that's the worst case condition. So 5th, you calculate the 5th harmonic voltage, the 7th harmonic voltage, the 11th harmonic voltage. We're making an assumption that all the peak values of voltage are in line with each other. So the peak of the 5th, the peak of the 7th, the peak of the 11th, and so on, they're all equal to each other, or they're all in phase with each other, so the phase angles are the same, so that we get the worst case condition, we get the highest peak voltage. We're testing peak voltage, and incidentally, when you do harmonic filter design, generally peak voltage is the limiting factor. That's what we have found in most cases. Peak voltage determines the rating of the capacitor. Not always, but for most filter designs, that would be the case. Another thing to look at is the RMS harmonic current. We're just taking the sum of the squares of the harmonic current flow into the capacitor, and we're making sure that we're at that 1.35 per unit level. We want to make sure that we're always below that 1.35 per unit level for the capacitor. And typically that's not a difficult item to meet. Same with rated kVAR. We're calculating rated kVAR. So our spreadsheet tool does this. We put in the harmonic current that we expect in the filter, or more really the real way of saying is we put the harmonic filter current ratings in the system. So we're coming up with a harmonic filter current rating. What is the fundamental current rating? What's the 5th? What's the 7th? What's the 11th? What do we want to tell our customers that the harmonic filter is rated for? And those are the values that go into our spreadsheet. Those are the values that are used to choose the actual fundamental voltage rating of this capacitor. And again, you want to be very conservative. You want to be very conservative because you're not going to pay a significant amount of additional costs for that capacitor for going up in voltage. But you do pay more. As you go up in voltage, you need more kVAR. More kVAR means more money. So when you purchase capacitors, and this is a chart from Eaton, and you can purchase capacitors with what's called different duty ratings. You can buy standard duty, heavy duty, extreme duty, and Eaton refers to these as their standard duty, heavy duty, and extreme duty. GE's got a similar system, and so does ABB, a similar system. But these are the key ratings for the capacitors that are going into our equipment. They're either C22.2 for Canadian standards, the IEC 60871, or IEEE standard 18. One of those standards are being used to come up with the basic duty ratings. The key that you want to be careful about is that when a capacitor manufacturer tests the capacitor on its assembly line, they're basically testing against the standard duty value, the base value, what the standards require. So you can ask for a heavy duty design, but it doesn't mean that the capacitor had came off the assembly line and was tested at 125%. So if you really want to make sure that you're getting a capacitor that carries its actual rating, you want to buy standard duty rated capacitors and bump up the voltage. Okay, so this is one thing to think about. One of the key differences between standard duty and extreme duty is the temperature rating. Okay, so the extreme duty can go down to -50 C. This is a factor up in Canada. When we're supplying up into Canada, we're making sure that the capacitors are chosen based upon -50 C because it does get that cold up there. Impulse rating, that's the impulse rating of your system. So if it's 13.8 kV, you're going to buy a capacitor that has a BIL rating of 95 typically. Now don't forget that you have altitude. You got to worry about altitude when you're in the mountains above 1,000 meters. There's going to be a D rating that you have to apply to make sure that you apply that D rating. And so typically we're specifying kVAR and voltage. kVAR, voltage, and pulse level, and kVAR, voltage, and pulse rating, a number of bushings is all that's required. So not a whole lot of things to specify there. So the standard ratings for capacitors, this is a list of those standard ratings, and the voltages for standard medium voltage capacitors will go from 2.4 kV kind of up through 20. It shows 22 kV here, 22.8 kV. All right, we got a question.
Yeah, Paul from Christian. He's asking if NEPSI's ever requested the manufacturer to provide type test reports for capacitors. When would it make sense? I know we have, but feel free to add some more info there.
Yeah, so good question. We do get requests from time to time for type test reports. I could tell you that if the capacitor has not been type tested, the one that's being specified or the one that we're requesting, it does carry a significant cost. There's a significant cost for the type test. But these manufacturers have type tested the various sizes of their capacitors, but if you actually want the exact capacitor that you specified, and harmonic filters were often going to an oddball rating. We might be going with, let's say, 350 kVAR or 375 kVAR capacitor. The manufacturer may not have built that capacitor, so to ask the manufacturer for a type test on that specific capacitor can be very costly, like on the order of $20,000. So we would typically request that the type test of a similar capacitor, similar design, and we would use that for such a request. To date, we have not had to supply a type test for what I would call a non-standard capacitor. And for the most part, a lot of the designs that we do follow use non-standard capacitors. Good question. So These are the voltage ratings and the kVAR ratings for the capacitors. They're the standard rating. You can ask for basically any kVAR rating you want. Obviously, as you go up in kVAR, the can is getting bigger and bigger, so heavier and heavier. There are some limits for which the supplier of the capacitor, typically around at the 15 kV level, you're looking at maybe 600 kVAR, and at the 2.4 kV level, you're looking at just 200 kVAR per can. So, depending upon the voltage level of the capacitor, you're able to get a certain size can. You don't pay a significant amount of cost to go from a standard capacitor to a non-standard capacitor. There are no manufacturers out there that we know of that are stocking standard capacitors. So you're not getting any advantage by going with a standard capacitor over a non-standard capacitor. The other thing is the mounting arrangements will change from one capacitor supplier to another. So when you're into a standard design, you're into that manufacturer's standard design. You're not into a standard design that works across the board. So you have to choose a supplier, and you're choosing a kVAR. So if your filter design comes up with a non-standard voltage rating, non-standard kVAR rating, then ask for it. And you'll get it, and you're not really paying a premium for it. All right. They have capacitors in North America. The IEEE standard, basically the CSA standard, both dictate that your capacitors will discharge in 5 minutes. So there's a discharge curve associated with it. They insert that resistor inside the capacitor itself, like you see here. And when you de-energize the equipment, it will take 5 minutes for the capacitor to discharge. So that's what we show here. Okay, yeah, we've got some typical weights here. Let's go through some typical weights. All right, here we go. The capacitors, you can see kind of here, this is Mark installing a capacitor into our equipment. The weights can get quite heavy, and this is just some representative weights. We have a philosophy, we like to go with larger, heavier cans and try to minimize. The whole purpose of a metal closed system is to reduce the size of the equipment, so don't be afraid of specifying a higher rated capacitor can. It helps to shrink the size of that metal closed system down, and that's really one of the key advantages of the metal closed system, decrease the size of the system. So we're up in this 100 to 150 kVAR range, but really for a metal closed solution, you're able to pick that capacitor up and bring it in and set it into the enclosure. Very easy to do. And it's a key advantage of it is that you're at ground level, you're picking the capacitor up, you're walking it in or dragging it into the enclosure, and you're mounting it inside the enclosure. So a very easy thing to do. When you look at the reliability of a capacitor, this is from ABB's presentation, the failure rates are very, very low. And if you properly rate the capacitor in the harmonic filter, you could expect failure rates of less than 1 in 5,000. So it's really very good failure rates. And this is data as presented by ABB once again. So less than 1 in 5,000. So if you think about, well, go with a conservative design. Say the system requires 9.54 kV. Instead of going 9.54 kV, go with 9.96 kV. And your failure rates will be even less than 1 in 5,000. So always think about adding some voltage to the capacitor. It's going to bump up the price a little bit, but it's going to even increase the reliability further. And in critical process plants, reliability is important. If you take a capacitor offline, you potentially have to take the filter offline, which can also potentially require that the plant be shut down. So always think about what is the ramifications for a filter failure. And the filter failure could be as simple as I operated the fuse because of a failed section within the capacitor, right? So it's important to try to design filters so that they're very reliable. The capacitor banks, there's always some type of blown fuse detection built into it. We talked earlier about a single-wye connected bank. That's actually shown here. we put a PT in the neutral. We're looking for a voltage here, a neutral to ground, to determine if a fuse has operated. So under normal situations, phase A, B, and C, the capacitor values are equal, the reactor values are equal, and therefore the neutral to ground voltage will be 0 volts. If instead I operate one fuse and I create an imbalance within the capacitor bank itself, I will get a neutral to ground voltage that can be detected with a neutral PT here. So that's called neutral voltage detection. I know for a fact that we have a tech talk, one of the early tech talks between 1 and 10, we talked about neutral voltage and neutral current detection. So I encourage you to go back to one of those tech talks if you want to learn about neutral voltage and neutral current detection. On the left here, what we do is we split the capacitor bank into two individual Y-connected ungrounded capacitor banks, and we run a connection between the neutrals of the capacitor banks, and we put a CT in the neutral, and we detect current flow. When there is an unbalance between the two Ys, between the one capacitor bank and the other, I will get a current flow. And it's that current flow that would indicate that I have an unbalanced condition, and that unbalanced condition is causing current flow. And we have on our website a tool, okay, go to the resource section on our webpage. There's a spreadsheet tool on our website that will help you calculate what that neutral current is for medium voltage cap banks. We do prefer the Split-Wye connection. We highly recommend it. And the reason being, one, is in this system here, if I have an external line to ground fault, so say I'm on a distribution system and out on a feeder there's a line to ground fault, there is an automatic neutral to ground voltage shift that this relay is going to see. And if you have a line to ground fault somewhere out in a distribution system, that neutral shift could cause a false trip inside our filter bank, okay, or inside a cap bank for that matter, if it were a cap bank. So that is one reason we prefer a Split-Wye arrangement like this. You will not get that spurious trip. Okay. The other reason is that the switching device, and we don't show a switching device here, but typically up here there's a breaker or some type of switching device. The switching device will see a higher recovery voltage with this type of an arrangement. When this switch up here opens, you have trapped DC charge on the capacitor down here. That trapped DC charge will want to discharge through the transformer here, and that discharge of current through that transformer, because remember the transformer's got high impedance for 60 hertz or 50 hertz, but to DC, that trapped charge is a short circuit, and you get a spike, just like you would in the coil of a car. You get a spike, and that spike can cause restrike, within the capacitor bank and the switching device here, and that restrike can result in capacitor failure. So you inadvertently put more duty on the switching device when you go with a neutral PT to detect blown fuse conditions. And so we were talking about the formulas. Our spreadsheet tools again utilize these formulas. These formulas can be found in the IEEE standards, and unfortunately I did not reference it here, but there is an IEEE standard that we referenced earlier at the beginning of this presentation. You can go to that standard to come up with these formulas. So let's talk about tuning reactors. So we covered capacitors. We'll go through tuning reactors. By and large, metal closed systems use iron core reactors. Open air systems use air core reactors. So that's our first key differentiator. We'll talk about that. But these are the standards that cover iron core reactors. And there's really not a standard that specifically addresses all the issues and tests required for harmonic filter reactors. Typically, it's pieces of various standards that are utilized to define the tests required for iron core reactors. But if there's anything that's critical in a harmonic filter, it is the iron core reactor. I can't overstress that. The most difficult part in the design of a harmonic filter is the iron core reactor. It's not to be taken lightly, the design of that and the selection of the manufacturer of that iron core reactor, and also the ratings of the iron core reactors. So we had another tech talk that talked about iron core reactors. I would recommend that before you specify iron core reactors, go back and watch that presentation that talks about iron core reactors. It would be good for you to do that. So air core reactors, you're going with an open air filter. You basically are dictating what type of filter you have if you want an air core reactor. And iron core reactors, you're always going with a metal close design. So iron core reactor on the left, really the key difference here is that the iron is trapping the magnetic field. All right, there is no external magnetic field on an iron core reactor. The inductance is developed in air gaps that are embedded underneath the winding of this reactor. To use a distributed gap type design, kind of how we show it here. Okay, and that determines and makes for the inductance of the reactor. You can have single phase iron core reactors and three-phase iron core reactors. And I think I'll touch upon that in a moment. Here we're using a floating core design. It means that the reactor is put up on insulators. And if you were to go through the calculations, what you would determine is that the voltage drop across a harmonic filter reactor is about 1 over n squared, 1 over the tuning point squared times the line to neutral voltage. So a fifth tuned filter is just a roughly maybe 5% voltage drop across the reactor. So therefore, there is a advantage for putting reactors, single-phase reactors, up on insulators. It means that the majority of the voltage drop is dropped across the insulators rather than across the windings. Okay, so it adds to the reliability. The same thing is kind of being done here with air core reactors. If you think about the webbing here, could be translated to the core over here. The core here actually holds the winding, and here the webbing is wrapped around the coil is wrapped around the webbing. So they are attaching basically the coil to the webbing. Okay, and then the webbing and the whole structure is supported on insulators. So they're elevating the voltage of the webbing here to the voltage of the winding. And the same thing is being done over here. The winding is being tied to the core, and they're elevating the core. The only difference is that the iron core is also conducting the magnetic field, where in an air core reactor you're using air. Because you're using air to develop the inductance, you need a lot more turns. So typically these reactors are very large in diameter, and they're very high, and they have a very high magnetic field around them. So these are things that you need to be concerned about. So we kind of go through what the advantages and disadvantages of the iron core and air core design. No iron core reactors, there's no stray flux. They are shipped installed within the filter system. So if you go with air core reactors, the reactors are so big, there is no shipping it as part of the harmonic filter bank. It's shipped separately and installed on site. The lead time for iron core reactors is typically 6 to 8 weeks versus air core reactors. We're down in that 26-week lead time, so much longer lead times for air core reactors. Because the iron core reactors are put inside the enclosure, the reactors is well suited for high wind and high seismic areas. Air core reactors are typically stacking them up inside the substation because they're high. They're not well suited for high wind and high seismic type conditions. So there are some disadvantages. The key disadvantages of the iron core reactor is that it can saturate. Okay, if it's not properly designed or specified, it can saturate. And this kind of goes back to a design philosophy that NEPSI has, which is to over-specify that iron core reactor to make sure the saturation is not an issue. We had a tech talk a couple sessions ago that we talked with a consulting firm about the advantages of making sure that you have linearity up to 250% of its rating. So something to to be specifying. So iron core reactor is a big one here, so they can get quite large, these iron core reactors. Incidentally, it's one of the reasons why you want to over-specify on them, because the removal from the system is more difficult. You have to bring a forklift into the equipment to lift them out. So it's a pretty big task, and you're not paying much for it. So let's go through here. Three-phase reactors. The difference between single-phase reactors is we got just a single phase, one winding on the core. The core is elevated in potential, and it takes 3 single-phase reactors to make a 3-phase filter. When I go to a single-phase, a 3-phase reactor, I have a single core but 3 windings. So I got phase A, B, and C, and the inductance is formed between the 3 legs. There are some disadvantages associated with this 3-phase reactor. One is it's difficult to design the reactor to be to not be noisy. The design process is much more critical, and it's because we're sandwiching the gaps within each of these legs, and the tolerance must be kept very tight between phase A, B, and C. So when they clamp the core, okay, the pressure within the core structure must be about equal. If they're unequal, you can get a set of laminations, say in the middle leg here, if we don't have even clamping force because of the tolerances within the gap structure, we can get a louder noise. So that's the one thing. The other thing is the core is grounded. If it's a 3-phase reactor, the core has to be grounded, which means that we have full voltage between the winding and the core. Between winding and core, we have full voltage, and that means we're always stressing that insulation, and it's really critical on the reactor supplier at that point to properly design that 3-phase reactor, because now you have full voltage across the winding to core insulation. So this is a typical voltage stress diagram for a 13.8 kV system. Here we're just kind of showing we have the end coming here, we have a winding around a reactor core, and it goes to a capacitor. And what we're showing here is that the voltage stress from the winding to the core it can be much less, and it gains some advantage by tacking the midpoint of the winding to the core itself. And you can have a similar diagram for 34.5 kV systems, where the BIL might be 150 or 200 kV BIL. But the key here is for single-phase reactors, up here we show the voltage here is I think we're showing about 318 volts across the reactor itself. So there's not a whole lot of voltage there. So basically low voltage on the winding. So it's very reliable from a impulse and voltage withstand point of view. And it's 34.5. So this is from Hansang Mangold, their website. You can see here, this is a 3-phase core that's being developed here. But just look at this, the leg here. There is a lot of laminations there, a lot of laminations. And really this is a distinguishing factor when you purchase iron core reactors, is how large is this gap here. There can be a desire to reduce the number of gaps. That in itself reduces the cost. Okay, reduce the number of gaps, reduce the cost. But the quality of the reactor is not as good. If you have a larger gap, you have more stray flux. More stray flux means more heat. This is really a picture that can show you just how many gaps you can have within an iron core reactor. And these all need to be supported within the leg structure itself. So by having lots of gaps, it means that you're going to reduce the noise and you're going to reduce the stray flux that you have in the reactor. So the process of specifying the reactor itself, we use a spreadsheet tool again. And the harmonic analysis program is coming up with a harmonic filter current, and from there we're coming up with, well, what do we want to rate the harmonic filter at, and then from there we're calculating how much harmonic current flows into the reactor, and we're specifying the reactor to the supplier. So what I show here to the right are the key ratings that we would typically use. Let me see here. There we go. We will show what we're transferring to our reactor supplier. So it's a pretty simple process. We're specifying quantity. Do we want single-phase reactors or three-phase reactors? And typically, NEPSI is only supplying three-phase reactors up to the 15 kV level. Would be most of our designs. We will not go with a single-phase with three-phase reactors above that voltage level. Specify voltage. The reactor supplier wants to know, well, what's the system voltage? That helps them to determine the installation level. We want the BIL level of the reactor, the withstand voltage of the reactor, and then finally the inductance of the reactor at either 50 or 60 hertz, depending upon the fundamental frequency. Do you need taps or not? This is a subject that we could talk about, taps on reactors. Do you need them? Do you not need them? Our experience is that taps are never used. So typically, we would say we would try to avoid taps. To put taps into reactors is to make them more complicated. And then specify the ambient temperature. Oftentimes we see specifications specifying 40 degrees Celsius because that's a standard temperature. The reality is if it's a metal closed system, the ambient temperature should be set at 60. The outdoor temperature might be 40 Celsius, but the inside temperature, inside the enclosure, realistically is 60 C. So specify 60 C on the reactor. And then the temperature rise really is dependent upon the installation level. Is it a 220 C installation system or 150 C installation system? But for us, we oftentimes are going to a 220 C installation system, so we would specify a 115 degree C rise. One key thing I'm pointing out here is we got some margins up here. Very oftentimes, and I would recommend that you think about this, is that your fundamental current rating of the reactor should be specified at 1.5 times the actual current that we'll see during operation. And really, this helps to guarantee that you get the 250% linearity that we recommend. It also allows for the reactor to run quieter. It gives it less losses. And it helps to give you a much higher reliability. So putting a 1.5 multiplier on the harmonic filter and on those harmonic filter reactors will result in a much higher reliable design. But it costs more. And but in the end, you're not looking to specify or to have a harmonic filter system that is running hot, that runs noisy, or that is unreliable. So this is what we typically would give to our suppliers. Just a couple pictures, air core reactors. You can see here on the left, we got some air core reactors stacked up on an elevating structure. This is a requirement in North America that you have at least 3 meters of height, 9 foot 6 inches. And on the right here are some pictures of some air core reactors sitting at ground level. This is something you would not typically see in North America. And we're kind of running out of time, so I'm zipping through now. These are the air core reactors we're shown. When you specify air core reactors, you're going to get drawings back that have the magnetic field clearance lines, this MC1, MC2 line. And that distance is going to be quite big. In fact, it can be up to 1.5 times the coil diameter. So it would be no metallic parts forming closed loops within that 1.5 times the diameter. So this area here, realistically, sometimes can be 20 feet across, so it can be quite significant. It's really why the metal closed solutions are sometimes just 20% of the area requirement of an open air solution. It's because we don't have that magnetic field clearance issue that air core reactors have. You also have clearance issues in the radial direction, and that's what this is showing, that if you mount the reactors at ground potential, you got rebar in the ground, that rebar can heat up. So you have to be concerned about the heating effect of what's in the concrete underneath the air core reactor. So we're going to kind of burn through this pretty quick. High-pass filter resistors. Here we are putting a set of high-pass filter resistors on top of one of our enclosures. This is a stainless steel enclosure. The reason it's stainless steel is that the enclosure itself can get hot up there. We don't want paint on there that can blister or turn colors, turn brown because of heat. So we're using a stainless steel enclosure. There are no fans for this. We're looking at using just natural ventilation to keep their resistors cool. So this is our standard practice is to park them up on top. We use roof bushings up through the roof. It's important that you specify real roof bushings with both high voltage and ground shields built into that roof bushing. Okay, so if there's a failure point, you don't want to use simple pass-throughs. You don't want to use PVC conduit, anything like that. You don't want to use medium voltage cable through a tube because over time those can fail. So you want to specify a bushing that has both a ground and a high voltage shield built into it, basically a bona fide bushing. There are some standards, IEEE 57.32, but these standards don't directly apply to harmonic filter resistors. So in the U.S., the primary suppliers are noted here, but Post Glover and Avatron are the key suppliers. There is a stainless steel type resistor. It's a stainless steel grid resistor. So they are exposed directly to the elements inside this box, but there's not much that can happen to it. The typical ratings are maybe minimum of 20 kW per phase, but we oftentimes see the ratings go from 150 all the way up to 200 kW per phase. So you can see why it's important to not paint that enclosure. And if your filter design, as you're doing your harmonic analysis, is starting to get, and this would be maybe for a very large mine project, if you're starting to get up into that maybe 180 kW, 200 kW range per phase, it means your design should change. It really means that you have to take a different approach in your design because the ratings are getting a bit high. So we won't go through this in detail, but we do give the formulas here. Well, if I know what my harmonic filter current I filter in here, this is what the harmonic analysis program had predicted the harmonic current flow will be into the filter. We can use a couple current divider rules here to calculate, well, how much current flows through the reactor, how much current flows through the resistor. And from there, we're going to get I squared R. We're going to be able to calculate I squared R, what the actual losses are in this resistor. And this is the process. The resistor supplier wants to know what's the system voltage and what is the kW losses within the resistor. Okay, so the resistor is being based upon ohms, and ohms of the resistor, the voltage rating, and the watts. What is the watts? And you want to be conservative again when you're picking your resistor. Perhaps double the rating that what you would expect. So you would double the rating of what you expect to make sure that you have a lot of margin in your design. So the previous page was for a standard high-pass filter. This page here is for C high-pass filter. The formulas are slightly different, but we come up with the method for calculating the resistor losses. High-pass filter resistors, this is just a close-up view of it. We like this stainless steel grid resistor element as you see here. The spiral round wound resistors we do not like. We consider them to be less reliable, and it also is adding inductance into the filter resistor, which you want to avoid. You really want a pure resistance for your resistor. So just kind of a close-up of how these look. You can see that the resistance is really developed by conducting current through this complex path. They reduce the area basically of pinching off the current with the stainless steel and creating resistance. These resistors can get very hot, up into over 300 degrees Celsius. So we have other things in the future that we will be talking about. One of those would be designing flexibility into your harmonic filters. We oftentimes recommend that you design flexibility into your harmonic filter. That might be the ability to change the kVAR rating of the kVAR rating. It might be changing the kVAR rating of the stage, the tuning point of the stage, being able to tap the reactors to move things around. So we have another presentation that we will talk about in the future of putting flexibility into the filter to allow for the unknown, really is what it's about. So we're going to zip over to questions and see if we got any questions. Remember, the confirmation code is 987 for the PDH. I don't know how you can't have no questions. There's got to be questions. So next week we're going to be talking about sweep frequency resonance analysis of harmonic filters. So SFRA testing of iron core, well, not of iron core, but of harmonic filters. So we have a large harmonic filter system in our factory floor, and part of our Q&A at the end, during the FAT testing, we would do an SFRA test on our harmonic filters, basically to verify the characteristic shape of the harmonic filter. We know the shape from our harmonic analysis, from our simulations. We know how it should look. So we then take an instrument, an SFRA instrument, which is typically used for testing transformers. We're going to hook that to the equipment, and we're going to get a sweep, an impedance curve, basically, of that harmonic filter system. It helps to verify that we designed the harmonic filter correctly, that it matches the impedance characteristics based upon the harmonic study, and then it helps to confirm that it's manufactured correctly. We have found that this device, this SFRA measurement device that's used to test transformers, will determine or reveal errors in manufacturing, and that might be mislabeled capacitors, misplaced capacitors, reactors that are tapped incorrectly, even the resistors that are connected incorrectly. We will be able to see those things. Maybe a missing neutral within the capacitor. So it's really a very important test that all EPCs should be specifying. If you really want to make sure that your filter meets the specification, that is going to do what your study says it should do, then you should be specifying SFRA testing on all harmonic filter systems. So next week we will have Pete, which is a twin brother. You will meet him. He looks just like me. And one other person. We will go out to the factory floor, and we will do some sweep frequency resonance analysis, show how we do that, and show you how those results look. So till next week, thank you.